Chapter 5, page 10, Specific Rotation and Racemic Mixtures. We just saw in the last section that one of the properties of chiral molecules is that they can rotate light. If you have two different enantiomers, one will rotate light a certain amount in one direction, and the other enantiomer will rotate light the exact same amount but in the opposite direction. So to be able to tell which isomer that we have, we generally need to standardize how we're going to measure these compounds, and that is known as the specific rotation. What we do is to standardize it, we take this one formula right here. Now, I'm not going to have you doing any calculations with this, but I still want you to understand what the specific rotation is. It's the standardized conditions for measuring how much a compound will rotate light. It's done at 25 degrees and using the sodium D lamp for the light source so that we standardize the conditions. Then you observe how much the light is rotated and you correct that for the concentration and the cell length in case your cell isn't exactly 1 decimeter long or 10 centimeters. This all goes into this equation. Now, just by the way, 1 decimeter is 10 centimeters or 100 millimeters. So if you use a cell length that's not exactly 10 centimeters or 1 decimeter, you can still get standardized conditions if you put it into this equation. Individual compounds that are chiral are known and measured so that the specific rotation of many naturally occurring compounds are known. Now, what are racemic mixtures? Well, we just talked about specific rotation and we talked about chiral molecules. So, for example, let's take this S isomer right down here. If it's put into the sample container and corrected for its concentration and cell length, we find that the S isomer will rotate light plus 13.5 degrees for this specific compound, 2-butanol. The R isomer will rotate light exactly the same amount but in the opposite direction. Remember, the plus sign over here means dextrorotatory and the negative sign here means levorotatory. So the two different enantiomers, the R compound and the S compound, will rotate light the exact same amount but in the opposite directions. Well, this section is called racemic mixtures, so let's figure out what's going on with that. If I didn't have one pure compound, but I had a 50-50 mix of both of these in the same container, then one's going to rotate light in one direction, one's going to rotate light the exact same amount but in the opposite direction, and they'll essentially cancel each other out. We call a 50-50 mix a racemic mixture. That means that we have equal amounts of the D and the L enantiomers, or the dextrorotatory and levorotatory enantiomers. We can note this by putting little parentheses and saying DL, or the little parentheses and saying the plus minus. This will have no net optical activity because the two cancel each other out if there's a 50-50 mix. Another interesting point is that boiling points and melting points of these even mixtures might be different than the individual compounds. We've talked about melting point in lab. If you have an impurity in a sample, it will essentially change the melting point and make it lower and broader. So each of these compounds will interfere the enantiomers with how the other one melts.